Alright guys, this is Ms. Schneider and I am recording myself working the review guide for the spring final exam, Honors Physics 2017. I'm going to go through this as fast as I can for my sake and yours. You might want to take a little more time looking at it. I will warn you that this is pretty true of the review. It's true of the test, but it's largely conceptual. And it should be the biggest concepts from each unit. So let's just dive right in. Alright, number one, first unit is electrostatics. Number one, be able to use Coulomb's law of electrostatics and the law of ones to solve problems. Example, if the distance between two charges is doubled and the magnitude of the charge on one object is tripled, what happens to the force of attraction between the charges? So, this problem requires you to know two things. One, what Coulomb's law is, which is F equals K Q1 Q2 over D squared, where that's the electric force, that is a constant, Q is each of the two individual charges, and D is the distance between them. Then you have to know how to use the law of ones. For the law of ones, anything that's remaining the same is a 1. Since K is a constant, it's always a 1. Here, one of our charges is changing, but one is staying the same. So one of our charges is still a 1. However, you have to change the numbers if things are changing to represent the change. That was change. So the charge, one of the two, the magnitude of one charge is tripled. So to represent that, we put a 3 as that charge. Then the distance between the two charges is doubled. So we put a 2 for distance, and that's squared, because distance is squared. So the final answer is 3/4 here. And what that's saying is that there would be 3/4 as much force. So you do need to know how to use the law of ones. You'll be given this formula, but you have to know that Coulomb's law is that formula. Looking at that equation, what is the force directly proportional to? So force is directly proportional to charge, because as the amount of charge goes up, the amount of force goes up. How is the force related to the distance? It's inversely related, because as the distance goes up, the force is actually going to get smaller. And it's actually inverse squared, which is because the d is squared, because as the charge doubles, force goes down by 1/4. If the charge triples, the force would go down by 1/9. So that's the importance of the squared. Alright, question number 2. What is an electroscope and what is it used for? So an electroscope is a device used to detect charge. It has two metal leaves that repel if touched by a charged object. I'm going to draw a really crappy little picture of an electroscope. Sometimes they're square, sometimes they're in shapes like this, sometimes they're square, but they have some sort of rubber insulated top, and there's a metal rod that comes down. It has little thin metal leaves on it. You touch something to that metal ball at the top, and if it's charged, it'll make the leaves spread apart. If it's not charged, the leaves will just hang down limply. Number 3, name the 4 fundamental forces we've studied this year and list them in order of strongest to weakest. The studied this year is kind of strong because we don't really look at the nuclear forces. Pro tip, one of these is the nuclear forces. So, strongest to weakest. The strongest force in the universe is the strong nuclear. Strong nuclear force, which is what holds protons and neutrons together. Then we have the weak nuclear. Actually, I can never remember whether the strong nuclear or the weak nuclear is what holds protons and neutrons together, and then the other does something different. Not important. They're super strong, because if they weren't super strong, atoms wouldn't hold together and nothing would exist. That would kind of suck. Then we have the electromagnetic force. So that's the first one that we really spent any amount of time on. And then last but not least, we have gravity, which is the weakest of the fundamental forces. It only seems strong because we have a lot of mass, but you can overcome gravity pretty easily with electric forces or magnetic forces. You can have a balloon on your hair and make your hair defy gravity. Right. Next, number 4 says explain charging by, and then there's 3 means. The first is conduction. This is transfer of charge through direct contact. You end with both objects having the same charge. And it's permanent. Induction is the polarization of charge. Without direct contact. So they're just close to each other, not touching. So that's like if you have a rod that's positively charged, and you bring it near this sphere, it's neutral to begin with. All the negative charges are going to be attracted, all the positive charges are going to be repelled. So it's polarized, but within the object, the whole object is still neutral. It's not permanent, because as soon as you take away this charged rod, the sphere will just go back to being neutral. Last, you have friction. So this is literally scraping electrons from one object to another. It is permanent because you are literally moving the electrons from place to place by rubbing something together. And you end with your two objects have opposite charges, as opposed to conduction. So something gained an electron, something lost an electron. Alright, give the charges on each of the following. Electrons have a negative charge. Protons have a positive charge. And neutrons are neutral. There's not really a symbol for neutral. Alright, if an object gains electrons, it becomes charged negatively. This is a little weird because you're gaining something, but you're gaining something that's negative, so it becomes negatively charged. If an object loses electrons, it becomes charged positively. Positive. What am I doing with my life? Misspelling positively, apparently. Whew. Using arrows and words, explain how a test charge would move an electric field. So a test charge is always positive, So it's always going to be repelled by positive charges and attracted by negative charges. So if we had a negative charge that was creating an electric field, we would draw it like this, because that shows that the little positive test charge is being drawn inward. If we were going to draw the field around a positive charge, it would be outward because it's pushing the test charge away. It's like, no way, get out of here. And then if you had an electric field between two charged plates, like if you had negative plate here, positive plate here, the electrons would all be like, oh, let's go, or no, the positive test charge would be like, oh, let's get away from the positive, let's go to the negative. Oh, 8. Draw a strong positive charge and the electric field describing it. Do the same for a strong negative charge. So that's basically what I just did. And it's positive charge is outwards. I'm going to add lots of arrows because the number of arrows indicates the strength of the field. And then negative, they point inward. If we wanted to show a weak negative field, then we would have less arrows. So, like charges repel, unlike charges or opposite part charges attract, opposites attract. Describe grounding. Grounding is exactly what it sounds like. It's giving excess charge to the earth. And this gets rid of it. So something that has been grounded has no excess charge. Alright, so while I was turning the lights back on, I listened to what I'd recorded a little bit, and it sounds like my audio is kind of going in and out, which is really weird because I'm wearing a super dorky headset with a built-in mic, so the mic is always the same distance from my mouth, even if I'm like moving around. So I don't know why the sound is varying. It doesn't sound like it's making that weird clicking noise that it did in the last video, so I'm just going to keep going. I love you, but I don't have time to figure out what's going on with technology. Whew. Okay. We are done with electrostatics. Now we're at current. List the factors that affect the resistance of a wire and state how they relate to resistance. So things that are going to change the resistance of a wire are its length. This is in no particular order. It's the order I think of them. So a shorter wire is going to have less resistance. Number 2 is the thickness of the wire. A thicker wire is going to have less resistance. Length, thickness. Okay, sorry about that. I thought that this was the answer to the last one, but then I confused myself. It's just what it's made out of. Some metal is obviously what you want to make a wire out of. Some metals are better resistors than others, or are better conductors. If you're dealing with a wire, you want it to be conducting, not resisting. Like gold is a really good conductor, which is why they try to upsell like gold-plated wires and stuff. Copper is a really good conductor, so a lot of wires made of copper. Okay, number 2, draw the schematic representation of the following in an electric circuit. The two that we deal with the most are batteries, which look like this little series of lines. And then we also talk about loads a lot, although we're more likely to call it a resistor. And it looks like a squiggle or monster teeth. Technically, a load could also be a light bulb, which looks like that. But in this class, it's usually going to be a resistor. A switch looks like exactly what it says it is. Looks like that. It can be open or closed. A fuse or a circuit breaker is drawn like this, like a kind of squiggle. Yeah, really clear in my drawing. I know, it's beautiful. Hey, we're like 1/8 of the way there. Oh my god. Alright, give the units and symbols for each of the following. Let me get where you can see what I'm doing. Unit and symbol. So, current. The symbol is an I, logically. It's measured in amps. Resistance is R. It's measured in ohms, which is represented with the Greek letter omega. Voltage is V. These two make sense. And it's measured in volts. Yay. And then charge is Q. Not logically. And it's measured in coulombs, which I can never spell. Distinguish between a storage cell and a primary cell. How about we not? We didn't learn that, and it's not on the final. According to Ohm's law, how are current and resistance related to each other? So Ohm's law says V equals IR, which means that, so if voltage is staying the same, as current goes up, resistance must go down, or as resistance goes up, current must go down, which means they are inversely related. How are current and voltage related? They are directly related, because as current goes up, voltage goes up. Conductors have blank valence electrons, while the valence electrons of blank are tightly bound. Conductors have loose valence electrons, electrons that are willing to just wander off, while the valence electrons of insulators are like, I don't want to play with you. I don't want to trade electrons. Nope. Okay. A math problem, number 7. A portable compact disc player, oh geez, a Walkman, receives its energy from a 9-volt cell. The current used to operate the player is 135 amps. How much power in watts does the CD player use? So we've been given V equals 9 volts. I, current, equals 135 amps. And we're being asked for power. If you go to your handy-dandy formula sheet and you look under the electricity section, there is a formula that says P equals IV. So we just multiply. 135 times 9. That's what I have to do that in my head. And I am getting 1,215. That power is watts. I almost wrote joules. That would be wrong. How much energy in kilowatt hours would the CD player use to play a selection 3 minutes long? Alright, now we're looking for E equals energy. Energy is equal to power times time. The deal is here, though, that they want our answer in kilowatt hours, because we have our power, it's 1215 watts, and we have our time that's 3 minutes, but they want kilowatt hours. So luckily, to get from watts to kilowatts is pretty easy. We just move the decimal 3 places. 1, 2, 3. So that's going to be 1.215 kilowatts. And then, of course, we never want minutes. So to go from minutes to hours, we're going to divide by 60. So 3 minutes is 0.05 hours. And now we just multiply those. 1.215 times 0.05. And I am getting E equals 0.061 kilowatt hours. Okie dokie. Parallel and series circuits. State the 3 cardinal rules for series circuits. So when it says cardinal rules, it means how the voltage, current, and resistance behave. In a series circuit, voltage adds up. V total equals V1 plus V2 plus V3 plus any other voltages you have. The current is the same everywhere. I total equals I1 equals I2 equals I3. So it doesn't add up, it's just the same everywhere. And then the resistance adds up. RT equals R1 plus R2 plus R3 plus etc., etc., etc. Voltage adds up, current stays the same, resistance adds up. The 3 cardinal rules for parallel circuits. The first 2 just switch. So voltage stays the same. VT equals V1 equals V2 equals V3, etc. Current adds up now. So IT equals I1 plus I2 plus I3 plus etc. Resistance is the one that gets weird for parallel circuits. The more resistors you add, the smaller the total resistance gets. And the formula for that is 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3, etc. How are voltmeters connected in a circuit? So voltmeters, because we want them to show the same reading that you're getting everywhere else, they should be connected in parallel, because parallel is where voltage stays the same. Ammeters, if we want them to show the same current as everything else, we should connect them in series, because that's where current is staying the same. What type of circuit only has one path for the current? That would be series. In this type of circuit, what happens to the other lights if one bulb burns out? They all go out because the path has been broken. It's very sad. What type of circuit has multiple paths? Why, that would be parallel. It's almost like it has parallel paths for the current to follow. In this type of circuit, what happens to the other lights if one goes out? The others keep working. They might actually get brighter because now there's energy going through them, more energy that was. But the main thing is that they keep working. Number 5, practice using the rules to add resistors in series, parallel, and a combination circuit. Oh goodness. Alright, I'm going to draw some pictures down here. What is the sum of 2 30 ohm resistors in series? Let's label these A, B, and C. So in A, goodness, the lights. Oh, yes, I'm here. Alright, thanks. Here we have R1 equals 30, R2 equals 30. So we just add. R total equals 30 plus 30 equals 60 ohms. For B, the sum of 2 ohm resistors in parallel. Battery again. this time, jaggedy, R1, is 30. Another squiggle is a really terrible resistor, I'm so sorry. R2, also 30. This time, though, we have to use 1 over. Luckily, 30 and 30 have a common denominator of 30. So we get 1 over RT equals 2 over 30. You take the reciprocal of that. So RT equals 30 over 2, or 15 ohms. And then this is by far the most complicated one. What is the sum of 2 ohm resistors in parallel added to a 30 ohm resistor in series? So that picture looks like this. Let's say you have parallel, parallel, series. This is R1, R2, R3. You're going to combine these first because they're purely in parallel with each other. And then once you've combined them, you can combine that combination, which when I worked these in the unit, I would have called that like R12. You can add that in series with R3. So because we just worked it, we happen to know that R12 is going to end up being 15. So then we're just adding in series RT equals R12 plus R3. So RT is 15 plus 30 equals 45 ohms. You might want to go back and spend some time looking at the review and practice problems on those. Remember that all we care about in complex circuits is resistance. You don't have to worry about current or voltage or anything. Use the diagram to the right to do the following. Now we have a real circuit problem. So we make a chart with Ohm's law. E equals I times R. We have 3 resistors, so we're going to have 1, 2, 3, 4 rows in our chart. And we fill in the information we've been given first. We've been told that R1 is 2, so that's 2. R3 is 3. V total is the battery voltage, so that's 18. V1, because it's a cross resistor 1, is 6. So now we look where we have 2 pieces of information, or where we're only missing 1. Oh goodness, I'm so sorry, you haven't been able to see this whole time. This is what I drew. So I filled in V1, VT, R1, R3. We need to look for where we're only missing 1 piece of information. Right now that's I2, or I1. So I1 is going to be V1 over R1. So 6 divided by 2, which is 3. Now, this is where it being a series circuit is real nifty, because the current is always the same. So we can fill in that whole column. You can always do that for something. If it's series, you get to fill in all of the currents. If it's parallel, you get to fill in all of the voltages. And now we have a couple of options about where to work. We can go, all right, V3 must be I3 times R3. 3 times 3 is 9. R total must be 18 divided by 3. 18 divided by 3 is 6. Wow. That was a little special. How long it took me to sort through that. And then we're going to say, all right, 18 has to be equal to 6 plus something plus 9. 18 minus 6 minus 9 must be 3. 3 times something has to equal 3. It's a 1. The way to double check is that R1 plus R2 plus R3 should also equal R total, and it does. Yay! And then we can come back over here and be like, we know all of these answers. That is 3 amps. That is also 3 amps. And that too is 3 amps. That is 9 volts. That is 3 volts. And that is 1 ohm. Notice that we did solve for a couple of things that we didn't actually have to solve for. But I still think that the benefits of doing the chart, it just makes it a whole lot simpler. You don't have as much to worry about, not as much going on at once. So I think it's worth, even if you have to do a little extra work. Alternating and direct current. DC is current that only flows in one direction. AC, current that switches directions rapidly. In America, that's 60 times a second. Which type comes from a battery? That would be DC. And from an electrical outlet, that would be AC. Whew! Alright, let's take a second. We're finished electricity. That was the first 2 units of this semester. And some of those circuits were a doozy. Alright, magnetism. North poles. So, just like with electric charges, likes are going to repel and opposites are going to attract. So north poles are going to repel north poles, and north poles are going to attract south poles. What protects our Earth from cosmic rays? Our magnetic field. What natural phenomenon does this cause? I suspect that it causes a lot of things, but I'm pretty sure what this question is asking us about is the northern lights. And I misspelled north. I am on the struggle bus. I wrote northern lights instead of aurora borealis because I knew I couldn't spell aurora borealis, but it turns out I can't spell northern. Guys, it's been a long day. It's been a long year. You know that as well as I do. What element makes the best magnet? Iron. Iron has 4 free electrons, or unpaired electrons, so it is so good at being a magnet. Because every electron is a tiny magnet. It's spinning. Please stop me. What elements are in an Elinko magnet? That would be aluminum, nickel, and cobalt. It's from the periodic table things. You know. Goodness. Let's move on. Number 4, how could you make an electromagnet from a nail, wire, and a battery? This is a question test we really like. Back when we did performance finals, we would always ask about this. So you would wrap the wire around the nail, wrap wire around nail, and then run current from battery through wire. What are some things you could do to make the electromagnet stronger? You could get a stronger battery, so more voltage. You could get a pure iron core. Nails aren't usually pure iron. And you could wrap more wire. You're specifically wrapping loops of wire, so you could have more loops. What are some things you can do to damage the magnetism of a magnet? You can drop it a lot. Like, you have to drop it a lot of times from a really high height, but that will eventually cause the magnetism to wear down. And you can heat it up really, really hot. What does breaking a bar magnet in two pieces do? It gives you two magnets. It does not destroy the magnet. It's kind of like sorcery, like, now you have two magnets. If you divide both of those in half, then you have four magnets. 4 times more magnets than you started with, but they're 1/4 the size. Someone, please stop me. God, I don't even like listening to myself. An electric motor converts blank energy to blank. So, a motor. I'm having to stop and think through this so I don't get it backwards. A motor starts with electrical energy and converts it to mechanical. Makes something turn. A generator is the opposite. It converts mechanical energy from you turning something, from a water wheel turning something, from a steam turbine turning something, and turns that into electrical energy. So they're just opposites of each other. Faraday and Henry discovered that electric current can be produced by the motion of a magnet. More specifically, voltage is induced in a loop of wire if there is a change in the magnetic field in the loop. My main man Faraday here. I like Faraday. And also, yeah, Joseph Henry, whatever, lived in the United States. Discovered that you could produce electricity using a magnet, and this is called electromagnetic, these blanks are not big enough, induction. Electromagnetic induction. You're inducing an electric current by moving a magnet. When the magnet is plunged in and out of a coil of wire, voltage is induced in the coil. If the rate of the in and out motion of the magnet is doubled, the induced voltage doubles. So if you move faster, you get more voltage. If the number of loops in the coil is doubled, then the voltage doubles. If you have more loops of wire, it increases your voltage. The other one would be if you had a stronger magnet. If the magnet was twice as strong, then the voltage would be twice as strong. Don't get these 3 factors mixed up with the 3 factors for an electromagnet. People do that a lot. It's a no-no. I can't believe I just said that's a no-no. Alright, I think I'm going to stop here because this is getting on towards the stuff that we've done more recently. I will record some more of that stuff tomorrow. Whew, alright.